So today we'll cover transmission shafts. So what we will do today is we will basically first understand what a shaft is. So we'll start with the introductory video, and then we will see some of the formulations. So how do you basically design shafts? And then finally, if we can cover today, we'll talk a little about natural frequencies of the shafts. That's very critical because especially if you're using very high-speed shafts, especially in gas turbines and even steam turbines, any small misalignment, and if you are close to your critical frequencies, this can be really very destructive for the shaft. So I'll tell you how do you estimate those natural frequencies for different conditions, different loading conditions. We'll talk a little bit about that. This is what we propose for this thing. But before we start, I'll have a small video in which I'll basically talk about what is the shaft which we will, what are the applications of the shafts which we will design and which we will go through in this class.
A transmission shaft. Whenever we see a pump, lathe machine, IC engine, and gearbox, etc., we always find a principal rotating element in them. The principal rotating element is called as transmission shaft. It supports the transmission elements of a machine and transmits torque from one machine element to the other. Thus, we can say that transmission shaft is a principal rotating element of a machine. It supports the transmission elements and transmits torque. Note that transmission shafts have a circular cross-section. Depending upon the application, shafts are given specific names, although all application involves transmission of torque. Motion and power. Some of the specific categories of transmission shafts are axle, spindle, countershaft, and line shaft. Axle is a shaft that supports the rotating elements like wheels of an automobile. Rope pulley. Wheels of railway wagon, etc. It is either stationary or rotating and is not subjected to a torsion load. It is used for the transmission of bending moment only. Note that axle, which balances the bending moment and transmits torque as well, is called an axle shaft. Spindle is a short rotating shaft. It transmits only torque and does not support any rotating element. It is used in all machine tools, such as the small drive shaft of a lathe machine or the spindle of a drilling machine. Countershaft is a secondary shaft which is driven by the main shaft and from which the power is supplied to a machine component. It is used in multi-stage gearboxes. And line shaft is a long shaft used in workshops or industries, bearing a number of pulleys and other transmission elements to drive the different machines at the same time. It consists of a number of shafts which are connected in axial direction by means of couplings. The related term is what is a transmission?
Just give me a minute. I'll just switch over to the other one. Okay. So let's do this. Just 1 second. Okay, so everybody can see my screen now, right? So let me just start with this. Okay, so what we were trying to talk about today was the shafts primarily, right? So basically, let's start with. So basically, as you saw in the small video, right? Just 1 second, let me get to the, yeah. So the first one, the first activity why you need a shaft is for torque and power transmission. So basically, wherever you have a prime mover, right? You have a prime mover such as motor, turbine, right? The power has to be transferred from a motor, from a gas turbine, from an engine. This has to be transferred, right, to other parts. So if I have a engine, the torque or the power has to be transmitted to the wheels if it's a rear wheel drive, or it's a front wheel drive to the front wheel, right? It's a 4-wheel drive to all the 4 wheels. So you need a shaft to transmit the power and the torque. And then if you have a gas turbine, the gas turbine would drive something, right? It will drive a generator to create power, or a steam turbine. The steam turbine will go ahead and basically drive a generator, and generator will generate power. So wherever you have to transmit either torque or power, you would need a shaft. So that's the primary activity of a shaft. The primary activity of a shaft is to transfer torque and power. Most of the rotary prime movers, either motors or turbines, use shaft to transfer the power, right? And one of the key things is, for that you require bearings for support. I'll show you what kind of configurations bearings are, and in another few classes later we'll discuss bearings. How do you select the bearings for different applications? And shaft failure analysis is very critical. So basically, I don't know if you know that these rotating equipments can be very expensive. A simple turbine of a, say, of a aviation turbine. Aviation turbine is the single most expensive equipment in the plane. It can be 50% of the cost of the plane. So if you have some of the engines are pretty much the most critical component of your plane, right? So you have to understand that shaft, if it fails, right? Because if the power is given by the shaft, if shaft fails, it can also have implications on the prime mover. So your turbine can also, so if there is a misalignment or if natural frequencies are excited, the shaft failures can actually damage the very expensive turbines. So it's very critical to understand and design the shaft properly, right? So that's why we want to say shaft itself may not be that expensive, but the shaft actually connects to very critical components, both the generator and the prime mover. They both are very costly. So if shaft goes haywire, there is a chance that those expensive components can also be damaged. So you have to be very careful when you design the shaft. So shaft design is very essential. And in some cases, if you actually excite some of the modes, the entire rotary components can just go haywire. You can lose very expensive turbines and components. Okay, so you have to understand this it's a very important topic. Okay. Now, one of the things is the thing is that you have to select the right material for the torque. This we will talk about. Then you have to understand the geometric layout. How do you basically fit the gears, the bearings, and other components so that the shaft does what it's supposed to do. Then you have to basically design it for both, for static and fatigue. So whatever fatigue concepts which we have studied in the previous class, shaft is the classic case for the fatigue application, because shaft inherently rotates, right? The moment it rotates, it will have cyclic loading. Any small eccentricity and it will have cyclic loading. And even if there is no eccentricity, by virtue of rotation, what will happen is if it is under load, there will be stress reversals. So it will not only have bending moment, so it will have both torsion and bending. And you'll have to design for fatigue both in torsion and bending. I will basically give you some of the formulations for how do you take into account both bending and torsion, and you design it for fatigue. Then shaft deflections are also very important. The bending deflections, the torsional deflection, the slope at the bearings, because at the so basically what is the kind of slope will define what kind of bearing you have to use, right? So if the slope is not very close to zero, if there is a finite amount of slope at the edge, then you have to use a different kind of bearing, right? If there is a thrust loading, you have to use different kind of bearing. If there's just pure radial load, then you have to use different kind of bearing. So the shaft deflections actually help you identify what kind of bearings you have to use, and you have to design in some cases when you have short shafts, especially in spindles, like your lathe spindle. So actual lathe spindle is a very short shaft, but then you will have to design it for shear deflections because there will be huge amount of transverse loading there. And then other important concept is critical speeds and natural frequencies. So basically natural frequencies are very important, because if you run any rotating equipment at natural frequency, you run the risk of damaging the very expensive component. So as I said, the small process turbines which are there in process industries, those cost 50 crores. Imagine what planes would cost. Plane turbines can cost you a few $100 million, right? So that kind of a component, if you run at natural frequencies, you run a risk of damaging the rotating equipment. So you need to understand that what will be the critical frequency of the shafts and try to avoid it. That's very important. For any rotating equipment, understanding the critical speeds is a very important concept. So I'll give you some first order approximations. How do you decide what will be the critical frequencies, and some of the discussions, not very detailed, but both via finite element modeling and analytical modeling I'll share with you in this class. So shaft material, as you know, so deflection is primarily controlled by geometry, because typically your deflections, it can come from your loads, the other it can come from misalignments also. So deflections will be there, and as we know that strain is a geometric parameter, but stress is a material parameter. But if you understand this, that sigma in most of the bending application my/I, right? This you have done it. I'll derive it very quickly today just to show you how it comes, and also the torsional thing I'll derive a little bit. I have discussed it off and on in other places, but this today I'll do a quick derivation and then basically come up with how do you decide what kind of stresses will be there in a shaft. Now my question is this: if you see stresses are material independent, right? If you see here, is that true? I want to answer from you, because moment is what I'm applying. Sorry. Moment is what I'm applying. Y is what is the maximum Y would be basically the shaft diameter divided by 2. So they say basically D by 2 will be Y, and I is also a geometric parameter, pi D4 by 64. So if that is true, then stress doesn't depend on the material, does it? Can somebody answer this question for me? can use your chat boxes to say whether what I'm saying makes sense or not. Does it make sense? What the statement which I'm arguing, does it make sense that sigma is not a function of material? Can I make that statement? I've given you the equation. Everybody agrees that the equation is correct, right? Everybody agrees the equation is correct? Yes or no? What I'm saying is I've given you, that's the fair argument. Strains will be independent of material, I can agree. True. But here I'm giving you a formulation where I'm showing it that sigma is equal to my over I. What you're saying is correct, that strains are independent of material. Okay. Stresses are not independent of material. That's a very valid statement. But what I'm showing you here is sigma is equal to my over I. Show me where is the material property. Very good. Very good. As long as there is no yielding. Right. Very correct. So this is what I wanted to hear. The material property comes in the yielding. If the yield stress is low, right? If sigma y is high, right? I can actually use basically a thinner, so I can use a low I material, if you get me. I can use a smaller shaft. I can use a smaller shaft for if my sigma, so let's assume that I have two materials. In one, sigma y1 is greater than sigma y2. Right? What it does, it gives me the freedom. It gives me the freedom that the sigma y1 can have a smaller I. Smaller I meaning smaller diameter. So I can basically transmit till yielding. That's a very correct answer. This is exactly what I was looking for. So material comes into play only when it yields. If it doesn't yield, you don't see this. But the problem is you're designing the thing. So you have to take into account for yielding, right? Because you'd have some factor of safety, and your what kind of moments you can transfer will be function of where it yields. That's the limiting factor. It's a very correct answer. So basically, you are right. Traditionally, strains are independent of material. Stresses are, because you see epsilon is some geometric parameter, and sigma is E epsilon, and E is a material property. That everybody understands, and it's a very good argument. But here what I showed you was that in bending, you typically say just my over I, and none of these do not have any material property. The material property kicks in only when it comes to yield. Okay, so yield is the property which actually defines under what condition, what kind of shaft I have to use. So basically, if I have a shaft less than 3 inches, I'll use cold drawn steel. And if I have anything more than 3 inches, D greater than 3 inches, then I will use hot rolled steel. Any ideas why I'm not using cold drawn more than 3 inches? Any ideas? Why am I not using a cold drawn thing in ever 3 inches? What is stopping me? I should. So first question is cold drawn better or hot rolled is better? Which one is better? Just a guess. What do you think is better? Cold drawn or hot rolled? Which one will have better properties, superior properties? Anybody? You have done all your manufacturing courses and all those. Cold roll, right? Very good answer, cold roll. But why do I not use cold roll for 3 inches? Everybody right. A lot of people are saying cold drawn, cold roll. Very, very good. Yes. Very good answer. Anything cold drawing more than 3 inches will be a nightmare. The forces required will be so high that drawing will become almost impossible to do. So that leaves us, for larger dimensions, it leaves us with hot rolling process, which is doable. So that's why I used hot roll. And after doing hot rolling, for all large sizes, we have to machine it properly, right? And for load production, again, we do machining. For high production, we do forming. That's something which is a rule of thumb. If you have large numbers to produce, if you are producing crankshafts by millions, you forge it, right? Because forging is inherently a very expensive process because you need dies, you have to make those dies, and the dies need to be hardened. Then when you do hot forging, then you'll have to do a series of other downstream processes, right? So all this is a very cost intensive process. Okay. So that's what it is. Now, once you have made the shaft, you have to lay out the shaft in a certain fashion. The shafts will need to have a bearing because you have to support the shaft. So for supporting the shaft, you will need bearings. For supporting, you need bearings. And then for transmitting, you'd need pulleys, gears. So all this need to be accommodated, and you have to design a shaft layout. So one of the things is how to lay out the shaft so that we can have all these components. So you can have axial layout, support the axial load. You need bearings, you need gears and sprockets to transmission. And then you also need to think about assembly, disassembly. So when I design something, I have to take it out for repair, for maintenance. So the whole thing should be laid out in such a fashion that it is easy to take it apart also, right? So these are some of the things when you design a shaft, you have to think about those layouts, right? If you are in your project, if you are doing something where there's power transmission involved, so the entire thing needs to be thought about. How am I going to support the shaft? Where will I keep the motor? How do I transfer my power from my shaft to another shaft if it's needed? Right. So all this you have to visualize and then basically put a proper layout, how it will be done. So typically the layouts are something like this. So see, these two are bearings, and this is a gear or a sprocket. You can mount a fan if you see. So basically, typically what you do is you would need to support at least bearings at two places. If it's a reasonably long one. If it's a very short one, then a single bearing would do. You can have bearing at one location and have a cantilever thing, but it's only for a very short shaft. For long shafts, you will have to have at least two. In some cases, you will have to support in between also if the deflection becomes very high, because you don't want lot of deflections. Larger deflection means there would be additional strains. Right. So this is what is some of the examples of how actual layouts of components are there. And then typically what happens is one of the things you have to understand is if your shaft, I'll discuss more when we discuss bearings. If the shaft has only radial loads, then you can have these ball bearings you can use. But if your shaft has any, so this can take only radial load. But what if you have any axial load? How do you support any axial load if you have? Any answers? So if there is an axial load, if the shaft can move along the axis, that has to be constrained, right? Any ideas how would you constrain that axial motion? If you want to have an axial motion, if the axial motion is like this, how do you constrain that kind of a motion? Very good, very good. Tapered bearings. You will have tapered roller bearings. Threads typically you don't do, because threads may not be a good idea because you need to have rotation also. So you cannot actually lock it. So that may not be a good idea because you still need the rotary motion. Okay, but tapered roller bearings are one of the answers for axial motion, right? So basically, if you see here, these are tapered bearings. If you could see, these rollers are tapered, and then there is a bracket to support to the frame. So you take the shaft, you take the bearings, and then there will be a frame on which everything will be supported. So these are just some of the examples how people do it. So here you see there is a bearing here, there is a bearing here. So there is a bevel gear. There is a bearing here, there is a bearing here. So one shaft will be mounted here and the other at 90 degrees. So it will be mounted like this. Okay. So this is for a bevel gear shaft. So you see how complex arrangement are there for bearings. Okay, I'll do that. So imagine I have a shaft. I have bearings here, right? I have bearings here. I have bearings here. These are just plain ball bearings, right? So what happens is if I have just say radial loading and I have reactions here, this bearing will work because there is only radial loading. All the loading is normal to the shaft. Imagine if I have some loads which are in axial direction, some FA axial load is also there. Then will this bearing work? This bearing will not work, right? Because now my shaft can come out of this bearing. Although these are snug fits, most of the bearings are shrunk fit, so they're very snug. It will not come out that easily. But if the load is high, it may. Eventually, it may. So what you do is you actually design something like this. So you will have some bearing like this, where there will be tapered roller bearings. So there will be tapered roller bearings. So what happens is your shaft will be like this. Your shaft will still be like this, but the bearing elements will be something like this. So the bearing element is tapered. So what happens is I'll actually show you when I teach bearing. I'll actually show you some real tapered bearings, how they look. So the bearings will look something like this. Here you see something like this. So basically what happens is you have this. So rollers will be so the shaft is still fit into there. The shaft is still sits straight, but the rollers are at a taper. So they can take some axial loading. So this is how the tapered roller bearings will look like. The rollers will not be straight, but the rollers will be at an angle. And this can take some of the axial loads. So if there is an axial load, they can bear some axial load. So rollers are tapered. Now, if they're not tapered, what will happen is they can come out. But here what happens is, since the rollers are at an angle, they are designed to take some axial loads. I'll show you when I teach bearings, I'll discuss more, and I'll show you how actually a tapered bearing looks. Okay, tapered roller bearing looks. But the way it is instead of having a straight roller, it will have a tapered roller. The roller will be at an angle, and it can take some amount of movement along the axial direction. Okay. So how do you connect the shaft, two shafts if you have to connect, or you have to connect shaft into a socket? How do you do it? You use keys. You can use splines. So this is a spline. This is a key. You can do set screws like this. Connect and put a sleeve, and then with the sleeve you tighten the set screw. You can have press or shrink fits. You can have press fit or shrink fit, and you can have tapered fits. So tapered fits are typically for if you have some axial loads. Okay. So it becomes difficult. So if it is tapered right, it will not let you move in one direction. So that's all what taper does actually. How many people know what is a shrink fit? Anybody can tell me what is a shrink fit? And what is the advantage of a shrink fit? press fit is not shrink fit. Press fit is you have to apply some load, but shrink fit is even stronger than press fit. Press fit is just you can apply some load and do it. Yes, very good. The nominal dia, yes, both answers are very right. Nominal dia is less than the shaft, and you heat the sleeve or the bearing, whatever it is, and it cools and fits and shrink it. Why would you use something like that? What is the basic advantage of using something like that? Why would I use a shrink fit? What is the benefit of using a shrink fit? Is there any benefit, or we just for the heck of it, since we can do it and make it really tight? Where would the shrink fit have some value? If it runs slightly loose, what happens? Yes. So the vibrations will be much lower, eccentricities will be much tighter. So for precision components, right, where you want centering to be, both the centers to be perfectly aligned. If I am, say, rotating, so I have machines in my lab which rotate at 150,000 RPM, 150,000 RPM. Now imagine if there is any misalignment, the whole thing will just go awry, right? I have no room for any eccentricities there. So what they do is they actually just make a perfect fit and clamp it very tightly. They don't do shrink fit because I have to keep on changing tools there. The shrink fit is not an option, but in a lot of these bearings, precision bearings, they actually do shrink fit. They will take the bearing, heat it in the oil, and put it on the shaft. So the centers are almost like at the same point. So you have similar centers. So there would be very little eccentricities, and that would lead to very little vibrations. Okay. And keys are one of the most common things where you do. One of the good things about key is you can design the key to be really soft, so that if anything fails, key is the first one to go. Right. And critical locations, as you all know, would be if sigma is equal to my over I, the maximum will be d over 2, right? Where the bending moment is large, or m is the maximum, where torque is present, or where stress concentrations exist. Because stress concentrations magnify the stresses, they amplify the stresses. So if they amplify the stresses, those will be critical place. If there is a notch, if there is a sudden change in the dimensions, that's where the critical locations would be. Okay. So now what I will do is, before I do that, I think all bending and torsion you guys know by heart, but still what I will do is I'll derive it from scratch just for the benefit of some of the students who would like how it is done. And then we both know that sigma is equal to my by I, right? And tau is equal to T rho varies from 0 to R by J. J is the polar moment of inertia. People use IP or J, right? So basically this is first equation, then this is second equation. I'll derive these two very quickly. And you know that there would be some stress magnification, because there can be change in diameters, there can be some shoulder effects. So you'll always have a factor for stress concentration, which is different in both bending and torsion. For bending, we call it KF. For shear, we call it KFS, which is torsion primarily. So I'll use KF factor in bending and KFS in torsion. Now, the other thing is, again, we talked about it, like what we showed in the loading, right? There will be the stresses, both shear and bending, will have a sigma max minus sigma min by 2, sigma A, which is alternating component, and sigma max plus sigma min by 2, which is the mid-range component. Both alternating and mid-range components would be there. So I will have sigma A and sigma M, primarily because of MA, because I will have a alternating moment and a mid-range moment. So I can do that. And same thing with also happens with torques. So I will have a amplitude torque and I will have a mid-range torque. Okay. So this you understand from the previous one, exactly similar to what we did it for fatigue. I'm actually adapting some of the fatigue concepts here. That's what we will do. So basically, before we do that, I'll quickly show how this all of you know, but I'll still very quickly try to do that. So typically what happens is I have this, right? I have this kind of, so when bending happens, pure bending, there is your neutral axis remains unchanged. Neutral axis remains unchanged. So your neutral axis is, if you see, this is rho theta, right? If this is theta and the diameter and because of bending, your beam will take a shape of a beam will have some curvature or some radius. So if the beam takes a radius of rho, the initial length will be rho theta right here, which I have shown here. Let me just go ahead and show it more clearly. So this highlighted portion in black is rho theta. Now if I go at some y distance up, this distance would be rho minus y theta, right? So this is LF. So LF is rho minus y theta and Li is rho theta. So epsilon will be, sorry. So epsilon will be, if you go ahead, theta cancels, you will get epsilon is equal to minus y by rho. Rho is actually the radius, so epsilon will be equal to minus ky, where k is curvature. Okay, so 1 by rho is curvature. So now what happens is, if I have to find out sigma is equal to E epsilon. So sigma will be equal to minus E ky. K is curvature, kappa, minus E ky is basically stresses. Now my bending moment will be, if I do sigma dA times y over the area, should give me bending moment. So my sigma is minus E, just 1 second, minus E ky dA times y, which basically means minus E k y square dA over area. This is nothing but I, minus E. So y square dA over area is moment of inertia, minus E k I is equal to m. So m by I is equal to minus Ek, which this is equation 1, this is equation 2, right? Ek is nothing but sigma by y, minus Ek is sigma by y. So m by I will be equal to sigma over y, right? So my by I is equal to sigma, right? So this I think you have done it probably in your 201, I don't know, or 206. Which one have you done it? Bending you'd have done probably in your second year or so, I believe. Okay, so this is something which you know very well. So this is where it comes from, my over I. Similarly, torsion also is very similar. What you have to do is, you have if you do a torsion at any section, the angle of twist is phi. So here it is 0, and as you go farther and farther from here, you will have phi. So this distance will be, if this is phi at that cross section, this distance is rho phi, and your gamma will be rho phi times the length L, because gamma is basically delta y by delta x. Gamma is 10 delta y. So this delta y is rho phi and delta x is L. So rho phi by L is your gamma, your shear strain. Now torque is equal to G gamma. All of you guys know, right? Torque is equal to G gamma. All of you guys know. So torque will be equal to G rho phi over L. Rho is the radius which varies from 0 to R. Rho varies from 0 to R. R being or 0 to d by 2 because I always use d by 2 everywhere, right? So 0 to d by 2. Okay. So basically here it happens like this. So then again, torque will be equal to tau dA into rho over the entire area of the cross section. So basically you have tau is G rho phi over L into dA into rho. So basically this comes torque is equal to G phi over L times rho square dA over A. This is nothing but J. This is nothing but J. So you will have T over J. T over J is equal to G phi over L. And G phi over L is what? Tau by rho. This is equation 1. So, sorry, let me make this. Yes. So this is equation 1 and this is equation 2. From this you can have T by J is equal to tau by rho. So basically you get tau rho by J is equal to tau. So this is your torsion equation. So this was your torsion equation and this was your bending equation. Now I know that I is equal to pi d4 by 64 for a circular cross section and J is equal to pi d4 by 32. Plug in everything there. So what you will get is for sigma A you will get K of ma 30 by 32 ma by pi d cube, and for torsion you will get 16 t by pi d cube. Any questions here? I'll just stop for a minute if you have any questions, and then we'll go ahead and start to apply some of the fatigue concepts which we have learned for shaft design. Any questions here? None? Okay. So if you have, just either stop me or type in the chat box. Okay. So this is clear, right? You will have authentic components and you will have mid-range components, right? Now, if you want estimate that what will be an equivalent amount of stress, because you will design something, right? So you need some equivalent concept right there. How do you get what will be the equivalent stresses? So I have a beam. I have a shaft which is subjected to some bending. So it will have some stress component here. If I look at it, because of bending, it will have some normal component, right? And it will have shear component because of torsion. So there is bending. So bending will give you some normal component. So the stress element will look something like this. It will have bending in axial direction. So this will be sigma zz if it is the z direction, sigma zz, and these will be the tau zy or whatever you want to call it, rz basically. Z, ZR. Okay, so there will be tau components and sigma components. Let me just not put any things here, just to make it simple. So there will be sigma and tau because it's a 2D stress state, right? So in this case, how do we get an equivalent condition for this? This is the state of loading. I know sigma is 32 m by pi d cube, and this is 16 t by pi d cube. How do you get how do we get equivalent condition? Any guesses about how do we get a condition which takes into account both of these stresses? What do we do? Any answers? None? Okay, so I'll show you how. So basically, if I have to get some equivalent stresses, how do I go ahead and do it? I have sigma A dash and sigma M dash equivalent. One way to do it would be that I do 2 sigma equivalent whole square. Use one Mises concept. Remember what one Mises is? One Mises says that sigma x minus sigma y whole square. Basically, it's it's easier to remember this way: sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square plus sigma 3 minus sigma 1 whole square is equal to 2y square. This is the easiest way to remember. But then in real condition, you will not know the principal stresses, right? You would know the actual stress conditions. So if you know the actual stress conditions, the formula is sigma x minus sigma y whole square, sigma y minus sigma z whole square, sigma x minus sigma z whole square, plus 6 times tau xy square, tau yz square, tau xz square. Now, and this is equal to some sigma equivalent. So now, in our case, what are the components which are there? There is only one sigma. Let's say, for sake of ease, we'll say there is only sigma x and tau xy. There is one shear component, and there is one normal component. Everything else becomes 0, 0, 0, 0, 0. So I will have 2 sigma square plus 3 tau square, because tau yz will become 0, tau xz will become 0, right? 3 tau square is equal to 2 some sigma equivalent whole square, right? So basically, if you see this sigma square, oh my bad, this is 6. Sigma square plus 3 tau square, sigma square plus 3 tau square is equal to this equivalent sigma equivalent whole square. So this is the equivalent stresses using von Mises stresses. So von Mises stresses, if you do, it will become root of sigma square, but this is true okay, it's acting up for some reason, but that's fine. This is what it is. So you get you basically get this. Okay. 3 tau square is equal to sigma equivalent whole square. So basically, this is what you get. So for calculating your mid-range and alternating stresses, you can plug in these relationships. This is for alternating, this is for mid-range. But now you have a composite relationship for both sigma and tau. Okay, let me go back to the full screen now. Okay. Just 1 second. Okay. And then we can use the same concepts which we have used. So now we have a lumped parameter, right, which takes into account both sigma and tau. So now I can use the same concepts which I did for this is modified Goodman, right, where I have sigma A by SC plus sigma M by UT plus sigma M by SUT is equal to 1 over N. 1 over N. So I can basically find out what will be the factor of safety for shaft design and what will be the diameter for it to have infinite life. Same concepts I'm applying in shaft design, right? So basically, similar approach can be taken with the fatigue failure criteria. Equations which you have distortion energy method, because I'm using distortion energy method because I have used sigma A, the equivalent sigma A and sigma M from von Mises, which is based on distortion energy. We derived in the class, if you remember, right? So this is distortion energy is the inherent thing with which we tied both the sigma and tau to one parameter, one composite sigma, and then use that in conjunction with Goodman. I can use Soderberg, Goodman, Gerber, and the ASME elliptic. All the concepts which we have done, I can do the same things for this. So I will design two things. One is the diameter required for infinite life, and what is the factor of safety here. So for Gerber, this is the relationship. Similar relationship which I had for Goodman, I can have for Gerber for factor of safety and for diameter also. And I can also design for ASME elliptic for Soderberg. Also Soderberg, although I'll not use because it's very, very conservative, don't need to use. But I can either do with ASME elliptic or I can do with the Gerber. But if I use Gerber and Goodman, I have to check for yielding. Remember, these two I have to check for yielding because ASME elliptic actually takes care of yielding, if you see, because it has SY built into it. So I'll have to do this. I'll have to figure out how do you do it for yielding criteria, right? So basically for rotating shaft, it's steady, alternating bending and torsion. Bending stresses is completely reversed, alternating, since the stress element. So basically if you have alternating bending and torsion, what you do is you put mm and TA equal to 0. This is what you put in that equation. And torsional stresses is steady. So torsional stress is constant if you have alternating bending and torsion, and bending moment is alternating. So your mid-range is 0, mid-range is 0, and here alternating is 0 for torque. So for condition where you have steady alternating bending and torsion, you have to put mm is equal to 0 and TA is equal to 0. Okay. If there are any questions, stop me, I can discuss it and then move on to the next one. Okay. Any questions? I can go back, revisit anything which you have not understood. I'll be happy to do that. Okay. So basically you have to do yield checking even in fatigue situation. I said Soderberg and ASME elliptic, they do it automatically. But for Gerber and modified Goodman, you will have to check specifically for yielding also, because they only check for fatigue. So you have to check for yielding. The first cycle, which I talked about, the first cycle yielding, that the way to do it would be that you basically get sigma max, use a simple thing. What you can do is you can do sigma m plus sigma a whole square, tau m plus tau a whole square, find out what will be the maximum sigma dash max, and then find out the yield by sigma dash max. So that's one way to do it. The alternate way is very simple. Just do sigma a dash plus sigma m dash should be equal to sigma m dash. That's another simple way to check it. Okay. But both ways are fine. So what you do is for yielding, you take both components, basically sigma max, which is sigma m plus sigma a, sum it up and find out the equivalent stresses, the one misses stresses based on sigma m plus sigma a, because sigma m plus sigma a is what? If you assume sigma max plus sigma min by 2 plus sigma max minus sigma min by 2, which basically means sigma plus m is equal to sigma max, if you remember this. Right. So that's why you put sigma m plus sigma to get sigma max here. You have plugged in values of sigma max and tau max both here. Sigma max and tau max. To find out what will be the sigma dash maximum, what will be the maximum sigma dash, and then check it with the yield. Then there are deflection conditions. So deflection analysis required complete geometry and loading information of the shaft, and then you basically find out what will be the geometry, and then basically you use right bearings to control it. Okay. This I'll talk more when I talk bearing design, so you don't have to worry about it right now. Okay. So determinant of deflections, people typically use finite element analysis. So if you are doing any analysis, any system design, use a FEA code to basically find out what will be the deflection. This is fairly simple to do that. Apply all the loading boundary conditions and you'll get. So the easier way to do it would be using an FEA. Okay. So I'll stop here for a little bit. If you have any questions, I'll go over it, or then I will move on to critical speeds. Any questions you guys have? I can go revisit it. Otherwise, then I'll move to that. How do you determine what is the critical speed for what conditions? Okay. What is KF and KFS? So if you remember from the fatigue, if there is a stress concentration, if there is a stress concentration, then you need to have a stress concentration correction factor KF. And this is different for bending and different for shear. So for normal and shear, there are two different parameters KF and KFS because the severity is different in different conditions. So this KF and KFS are needed to be applied if there is a change in the dimension, or there is a notch, so you will have automatically some sort of a stress amplification, and you need to account for that. If you remember, I actually showed you both in the numerical problem also, and also in the fatigue thing. Let me just go ahead and pull that up. Let me pull that up. Fatigue. So after all the modifiers, I actually showed you that. You read, you see this KF. So you see here, it says if you have for fluctuating load, there's a stress intensity factor, and the best approach to divide. So basically, KF should be applied to both alternating and major components, and wherever there is localized strain occurs, we recommend KF to alternating stresses, but KF has to be applied to both alternating and major stresses. And this KF is primarily because of stress concentration. And the moment you have a shaft, right, you will have something in the shaft, right? You will have a gear, you will have you will have a bearing in the end, you will have a pulley or something to transmit. It can be a fan, it can be something that is mounted on the shaft. So there will always be change in the sizes of the shaft. You cannot have a fixed. You'll never have a uniform shaft. There will be very steep changes in the dimensions in the shaft, and because of that, there will be stress concentrations right at where the dimension changes very fast. So regardless of what you do, you will have these changes in dimensions. So you will have to have this stress intensity factor, which needs to be applied to both alternating and mid-range components. Okay, did I answer your question? Yeah. So this is similar to what you do, but here it becomes more critical in the shafts. So just one more second, then we'll do some preliminary. So what I will do is, before I do this, let me just show you some stuff to just prime you up. I'll not do analytical stuff today. I'll just show you some nice FEA things, how people do modal analysis, and some videos. So before we do analytical components, let me just show you what do you mean by modal analysis of shafts. Actually, this is easier. I'll just move on to this. Okay. Okay. So basically what you can do is, if you have to do modal analysis of shaft, this can tell you what kind of, so you have a shaft, and then you can use, you can do the meshing, and then you can basically ask to do modal analysis. So what it can do is, it can give you all the modes, frequency modes. So it says that The first mode occurs at 0 frequency. The second mode occurs at 492. So basically what it does, it actually shows where the critical frequency of the shafts will occur and what kind of rotation will be there in the shafts. Let me just show you some of the videos which we have. No, not this one. So this is how the shaft will, this is how the shaft will deform in the first mode. The second mode, if you see, will look something like this. So every mode will have a different type of so see, this is the mode 2. So all these critical frequencies have a nature of how it deforms. So this is the second mode. The third mode will have something different. So this analysis is required if you are exciting those frequencies. If you give that frequency, the shaft will start to have that kind of a modal shape. See, all of them have a different kind of a modal shapes. So this can be done, and any system, right? This is just a free kind of a shaft, but if you have all the compliances, bearings, so it will have different natural frequency. And if you give that natural frequency, it will tend to have, in some cases, it is more dangerous than the other one. In some cases, there can be some twisting, there can be some bending. So it can be combined modes also. Okay. Oh. Alternating and mid-range sigma. I thought I did that, but I'll explain it again. Okay, let me just shift back to that. So how many people don't understand what is alternating and mid-range? Because we have done so many problems, and who doesn't understand? How many people don't understand yet what is the alternating and mid-range? If not, what I'll do is I'll actually, let me plug in this.
So the formula and calculation is something like
I thought that should have been very clear, but if it's not,
okay.
Okay, here. So basically, any stress loading, if I have, right? If you have any stress loading, your loading will, most of the things which we formatted in the beginning part of the fatigue course was for fully reversible. Fully reversible basically means that you have something like this. Something like this. Let me just go ahead and enter options. Something like this. Which basically means that my mean is 0. But any normal loading which you have, right, will be something like this. Right. So this kind of loading, how do we characterize? Right. This kind of loading or any kind of loading, you can have loadings like this, where mean is not equal to 0, where it's your amplitude is same, but your mean is non-zero, right? So all sorts of things can be there, but most generic will be something like this, right? This will be the most generic one, where you have some some random signal, right? But even in this signal, right? Even in this signal, I have a sigma min, I have a sigma min and a sigma max, a sigma min and sigma max, sigma max, right? So I can characterize any signal, because for any signal, any random signal which is varying in time, I can have sigma mins and sigma max there, right? There will be a maximum sigma min and a minimum sigma max. So I can formulate for that signal. In this case, let me just actually go ahead and I'll share this one, so this will be more clear. Okay. Okay. Just give me a second. Okay. So basically, let me go there. Right. So what I'm saying is, for any condition, how do I quantify this kind of a random signals? How do I quantify these kind of random signals? Because for this also, there will be a sigma min and a sigma max. So sigma min will be probably here. This will be sigma min, and probably sigma max is this or this. So let's say this is sigma max. For any random signal, I can characterize I can identify sigma maxes and sigma mins. So I can find out sigma A is equal to sigma max minus sigma min by 2, and sigma m is, so I basically need to know how do I quantify any random signal, right? So this kind of a signal, the worst case condition in this is this alternating and this mid range. Sorry, you get me? Did I answer your question? Or so the issue is, the physical meaning is that you are trying to find out what will be, where the mean range of your signal lies and what are the extremities. So you have to quantify the mean and extremities, because whatever data you create for fully reversible, because when you do the testing, you do fully reversible. But in real life, the loading has different connotations. Your loading can have anything. You can have any sort of loading. You can have loading like this. You can have loading like this. You can have loading like this. So for any loading, I need to be able to characterize the equivalent sigma m and sigma A, so that I can design it, so that I can predict a fatigue life for that. So I agree, in some cases what I will do is I will basically take the extreme conditions, because in this condition sigma max or sigma min occurs only at one location. Everywhere it is like maybe much lower than that. But still, you're designing it for the worst case condition. So you need to have some idea of what will be the mid-range stress of any signal which you have, and what will be the extremities, which will be the alternating components. So it's not only the formula, it's also the physics of it, is that you want to be able to say what are the extreme variations and where is the mid-range of your signal, of your force or stresses.
Okay, sir. Yeah, understood. Thank you.
Will it answer your question, Radha? Or still you have some doubts? If you have doubts, you can basically ask your questions.
No, okay, so that was what, like, I was understanding that sigma is sigma max minus sigma min by 2, but why it was so and what was the use of it was what I was looking for. Yeah. Thank you, sir.
Did you get it, or you still have some doubts about because I thought that we solve problems in fatigue here, and then we are going back to a couple of slides, couple of lectures back actually with this.
Yes, it is clear now. Thank you.
Okay, so is it clear, or should I expound a bit more on this? Okay. So any other questions? Anybody who has not been able to get that any of the concepts which we discussed today? Okay. Okay, so what I'll do is I will try and do a bit. Or let me just go ahead and do this. So we'll basically just talk a little bit about critical speeds, and then we'll discuss this stuff in next class. Okay. Okay, so the critical speeds which you need is basically you have a rotating shaft, and there's a centripetal force which is equal to the elastic restoring force, and the deflection increases greatly, and the shaft is set to whirl. So if you have at certain speeds, the shaft is supposed to whirl. So it starts to whirl, as in like there is a whirling speed, and this whirling speed is actually this is what it is. This is what is called critical speed. Critical speed. And below and above this speed, nothing will happen. But as you get close to the speed, then there would be issues. So the shaft dimensions, the shaft material, and the shaft loads are what govern this critical speed. Okay, I'll not derive anything today, but I just wanted to give you an idea of a critical speed. So the moment you get to this kind of a speed, all of a sudden there is your amplitude, this amplitude of vibration, it becomes very high. Becomes very, very high. And there can be resonance. Okay, this is where I'll stop, and then we will formulate a few things in the next class, and then we'll take it from there. Okay, I just wanted to kind of give you some idea of how do you do that, and this critical speed is extremely important in shaft design, and it can, if you don't take into account this. So typically, if somebody is using a gas turbine, what they do is typically you need so the gap, the operational gap should be between the two natural frequencies should be enough, so that you don't hit while operating, you do not hit the natural frequencies. So what they do typically in gas turbines is they actually operate between 1 and 2 or 2 and 3. So there is a wide gap between the two. So what they will do is when they start, they go very fast. So they pass the first natural frequency very fast so that it doesn't really dwell there. And then they would go ahead. If they dwell a little bit, then the shaft will start to vibrate very vehemently. So what they would do is they just ramp it very fast across that natural frequency. But for that, you need to know that, right? If you don't know, then you will damage your shaft. So a lot of these rotational rotary equipments, knowledge of rotor dynamics is very, very critical. Otherwise, you will end up destroying millions of dollars of equipment. So it's a very important concept to know how do you avoid those critical speeds and where do you decide my shaft will operate. So you will need to have wide range between the critical speeds so that you can operate safely within that regime. And by mistake, you don't hit one of those critical speeds. Okay. So with this food for thought, I will stop. And if you have any other questions, I'll be happy to answer again for 4 or 5 minutes. And then we'll meet in the next class. So anything which is not very clear, I would request you to either speak out or type if I have not answered the question satisfactorily. You can counter question, because that's one way to have a. So you need to have a discussion to be able to grasp the concepts. Okay. Monologues typically are not very useful in most cases. So any questions, I'll be happy to answer. If not, we'll see you next week. Any questions about your projects or whatever, I'll be happy to answer those as well.
So on Monday, we are supposed to submit the document only, right? Not the presentation.
Unmute yourself. If you're asking something, you have to unmute yourself. I don't think you have unmuted. If you.
So are you able to listen?
Yes, I'm able to hear you now.
So about the project, are we only supposed to submit the document or both presentation and document as
well? You have to do both. You have to submit the document, and based on that document, you have to make a small presentation, no more than 5 slides, and present it in front of everybody. So both the student community and the TAs and all of us will be present. We'll try to take 2 of these evening sessions to finish everybody.
Okay. Thank you.
Because I want you to also communicate what you are doing. So everybody should know what everybody is doing. It has to be a community learning experience, right? Because you are doing something, you need to share it with other people, what you are doing, what you learned. So it's a very good hands-on learning, has no substitute. It's actually the best form of learning there is.
Yes, sir.
Any other questions you folks have about the project or about any other concerns you guys have? I'll be happy to talk about it. So if not, have a good day, and then we'll meet next week. Okay. Thank you very much.